continue today then with Chapter 4, Lesson 5. As you can see from the title of this slide, we're going to be talking about triangles, which is not a new topic. However, classifying them by the length of their sides and the size of their angles might be a little bit. Here you see an example of kind of an interesting origami artwork there on the left. He's chosen that because if you think about it as two-dimensional, as we have on the right here, you can see samples of three of the types of triangles we're going to be looking at. Here's one. You got a name for that one? It will have a couple of names, as you will be able to see. We would call this an obtuse triangle. We'd also call this a scalene triangle. Oh, I'm sorry. That was wrong. Isosceles triangle. Isosceles and obtuse. One name according to the sides, one the angles. This one we would call a scalene triangle, and we'd also call it an obtuse triangle. And the one in the red, we would call that an equilateral triangle and an equiangular triangle. There are some other triangles in here that you'd be able to also take a look at and name. Let's get the actual definitions. Here they are. The more you hear them, the more likely you remember them. Definitions: a triangle is scalene if and only if it has no equal sides. You'll see the progression here. A triangle is isosceles if it has at least two equal sides. This comment turned into some questions in the problem sets today. At least two equal sides. With that wording, could it have three equal sides? A triangle is equilateral if and only if all of its sides are equal. So no equal sides, at least two, and all. These, of course, are used to name triangles according to the length of their sides. This next batch labels triangles according to the size of their angles. A triangle is obtuse if and only if it has an obtuse angle. Just one. You probably can figure out why. What if it had two obtuse angles? So you're trying to picture a triangle that would have one obtuse angle here and then another obtuse angle here. Well, we've used up our three sides. Doesn't look like we're going to end up with a triangle. Next, a triangle is right if and only if it has a right angle. Again, you'll notice a right angle. Here we had an obtuse angle. Again, try to picture a triangle. Boy, that is goofy. A right angle there. Now if we do another right angle here, we definitely have a problem, don't we? We don't have a triangle. Continuing down here, a triangle is acute if all of its angles are acute. So that one you can probably picture. Simple triangle, something like this. All of the angles, here they are, they're all acute angles. I'm not doing that on purpose. I don't know why that happens. So that would be an acute triangle, all the angles. And finally, equiangular. A triangle is equiangular if and only if all of its angles are equal. We have one theorem we're going to spend a little bit of time on here today. The rest we're just going to list and you'll work on them in the problem sets. What looks to be true about an isosceles triangle? If you remember that term from just a slide or two ago, isosceles, if at least two sides are equal. So here we go. So if you notice that these two sides are equal, what else looks to be true? That's the question. And maybe you saw it. If two sides of a triangle are equal, the angles opposite them are equal. We're going to work on this proof just a little bit. What would the converse of this be? Instead of saying if two sides are equal, the angles opposite them are equal. Yes, you probably have it. If two angles of a triangle are equal, the sides opposite them are equal. So let's take a look at proof of this. Oh, here I'm just marking these off. Here we have if two angles are equal, then the sides have to be equal. So here's the proof of that theorem. You'll be doing one in the problem sets exactly like, well, very similar to this. Instead of starting with two angles equal, like we're doing here, I'm going to back up. Let's just work with this. So here we have an isosceles triangle. Triangle BCD we're calling it. In order to do this proof, we're actually going to create another triangle right on top of it, exactly the same. You see penciled in there B, C, and D. We're going to slide it over and we're just going to flip it. So identical triangle, slid it over and flipped it. What equalities are true? Since it was isosceles to start with. So maybe you can start to see this angle B down here is equal to this angle C over here, up backwards C. Angle D up here on the top is still equal to angle D. That's the same angle. No flipping affecting it there. And then angle C is equal to angle B, and then they just run through the whole process. Side BD is equal to side CD, and so on around the triangle. All those equalities are true, and we have two triangles. So here's the proof that if two sides of a triangle are equal, the angles opposite them are equal. As I mentioned, one of the assignments, or one of the problems in the assignment set, very similar to this, but it'll say if two angles are equal, the sides opposite are equal. So take a clue off of this one. So here we're given, we have triangle BCD, in which BD is equal to DC. Simply tells us that it is an isosceles triangle. And we're supposed to prove that these two angles down here are equal. Because if two sides are equal, the angles opposite them are equal. So here we go, here's the start. We have triangle BCD and we've got BD equal to CD. Well, of course, the reason for that would be that it is given. Next, we're going to use this, what's marked up on the drawing up here. That angle D is equal to angle D. What allows us to say that something is equal to itself? Hopefully you've got the reflexive property there. Next, we can't really go anywhere with either of these anymore, so we're going to go with our next given, that BD is equal to CD. But that's kind of interesting because there's a CD here and there's a BD over here, so those two have to be equal, as do those two. So we feel like we can say that triangle BCD is equal to triangle CBD. Right now I'm going to pause a minute, see if you can get a reason for why those two triangles up here have to be congruent. You only have two choices, right? Hopefully you can think of those. We've got SAS or ASA. Which one? Hopefully you came up with SAS because we have two sides and the included angle on this triangle equal to two sides and included angle on this triangle. Now they're going to say that angle C is equal to angle B. Why can we do that? Well, I think I've mentioned once or twice that normally when you have a statement of congruence, it's telling you that all the corresponding sides and angles are equal. Our next step is going to be that. Angle C equals angle B. We're going to say that is corresponding parts of congruent triangles are equal. We've also called that CPCTE. Now that's interesting. We're saying that C is equal to B. But this B is exactly the same as this B over here. So we started with two sides equal and we proved that the two angles are equal. Theorem 10 is the one that you're going to run into in the lessons. If two angles of a triangle are equal, the sides opposite them are equal. In other words, if angle L equals angle N, then LM, this side, has to be NM, this side. And then finally, two corollaries. I think they're going to be easy for you to remember. An equilateral triangle is equiangular, and an equiangular triangle is equilateral. Let's see why they're corollaries. So if it's equiangular, let's start with this one. If it's equilateral, we know those two have to be equal. Well, if two sides are equal, we just proved that the angles opposite them are equal. So those two angles have to be equal. Oh, and it's equilateral to start with, so that means this side is the same as this side. Well, then the angles opposite them have to be equal, so that angle has to be equal to that angle. So hopefully you can see why it's a corollary. If it's equilateral, all the opposite angles are equal, so it's equiangular. And you can follow that same idea across with, if it's equiangular, if the two angles are equal, the sides opposite are equal. So there's lesson 5 of chapter 4. Let's get it going at the problem sets here. First part, we've got some givens here, and I keep changing the pen here because from now on, when you see stuff like this, it's going to be very helpful to mark it on your picture. So we're given that AB is equal to AD, and we're given that angle C is equal to angle BDC, this angle down here. So now before I even start, I can start to think, well, if two sides of this triangle are equal, then the angles opposite them are equal. So ABD, so I could say that these two are equal. And up here we've got two angles equal. Well, that would mean the sides opposite them, this one and this one, have to be equal. So we haven't even started answering the questions, and those are the kinds of thoughts you have to work through this. So copy the figure and mark it as I did. Which angle of ABD is opposite AB? So there's side AB, they want to know the angle opposite. Which angles have to be equal, and so on. Similar questions based on what we already talked about. This problem demonstrates the difficulties that you're probably going to have when triangles are overlapped. We have triangle ADC on top of triangle AEB. We have some givens, and that will help. We're told that AB equals AC. Let's work with that one first. What kind of triangle must ABC be? So we're classifying it, this time according to the length of its sides. We're also given that AD is AE down here in the given. Keep that in mind. So what kind of an angle is ABC? ABC, we're just talking about the angles here in ACB. Why are those two equal angles right now? That's the question. What angle do these two triangles ACD and ABE have in common? So looking at those two triangles, and it looks like that one up there. So there we have those two sides of that triangle with the pink angle up here. We're trying to determine number 10 here, why those two triangles are equal. There's a pretty big hint for you. I've tried to help out with the colors and the angles there. And then they follow with why is D, angle D down here, equal to angle E. Keep in mind what you just said in number 10. Spend a little time with the word isosceles here. Work through that one. When you get down here, where are the equal angles in an isosceles triangle with respect to its legs? So look at the legs, and where are the equal angles? Here's three little drawing activities. Think about what it means to be a right triangle. Can you make it isosceles and a right triangle? Scalene and isosceles at the same time. Obtuse and isosceles at the same time. Draw those. Building in San Francisco, if you've been there, maybe you've seen the Alcoa building. You can see a photo of it here. Lots of triangles in there. They're telling us that they're isosceles triangles. They've also drawn a little figure on the right, and you should mark that up with the givens. I've done that here. Now, before I even go too far, I can see these two triangles are clearly going to be what? New term we had a couple lessons ago, and you should be able to tell why, and that's going to be the basis of some of these questions. First of all, what kinds of triangles are they? Look at the sides or the angles. Why is 1 equal to 3? Again, those tick marks help a lot looking at the theorems. Think of Euclid's common notions here when you answer number 21. I repeated 20 and 21 at the top here, so we're moving ahead. What does this mean, do you recall? It's saying that ray LO is between ray LA and ray LC. It's between. Keep that in mind as you're answering number 22. Next, why are angle ALC and angle AOC? So ALC, we're looking at this angle up here, equal to AOC down here. Now they're asking about the two triangles. I think you ought to go back to a previous slide, a previous problem, that you'll get that. And remember, when you follow congruence, probably what's coming next, they're asking about these two angles up here, angle 1 and angle 2, what must be true? And that in itself suggests what LO does, that this ray LO right here does to this angle up here. And just kind of a thought question here. What happens if we were to draw AC? Get some of that out of there. Can you think of what might be true if you draw that in? Puzzle that out. Some church basements have shuffleboard on them. Maybe yours is one. We've got some questions here about a shuffleboard court, and there are definitely some givens. Again, you should mark those out on your picture. I would draw a figure. They don't tell you to, but it's helpful. And a question. What does it look like OD does to the three segments that it crosses? So they're looking at SB and HE and UL. What does it look like it does? Get rid of those. Let's keep going here. What relation do SB, HE, and UL appear to have? So again, we're looking at these three segments, what appears to be true about them. What kind of triangles do we have? Again, you have two choices there. You should consider, are we talking about their angles, or are we talking about their sides? Or maybe both. We're going to give you one measurement here. Angle F up here. 36 degrees. Now they're going to ask you about three other sets of angles. What can you calculate from that? This last one's a little bit tricky. Make sure you're looking at angle SUL and angle BLU, those two guys. If you get the previous ones, I think you'll get that one. Here's that proof I told you about. Now we're trying to prove that if two angles of a triangle are equal, the sides opposite are equal. Another proof, a complete proof of the theorem that we had, this corollary. If it's equilateral, then it's equiangular. This is a nice proof. Work this through. Think about what you know. We're trying to prove the corollary. That means we know Theorem 9 itself. So check back what Theorem 9 is. You can use that to prove the corollary. Kind of did that in the lesson. Proving corollary to Theorem 10 is the next one. It's going to be real similar to the previous. Going into the world of chemistry here, we have a hydrogen sulfide molecule. And there are some givens here. SH1 is equal to SH2, and it's been marked here. Oh, when I see that and I see this triangle, a couple things should occur to you. And he asks those, what kind of triangle is it? Giving you one measurement, he's telling you this. Find the measure of a couple of these other angles. And once you've done that, name the triangle based on its angles. So keep that in mind, not the sides, but the angles. Then he gives you a little bit more. Suppose that we know 1.34 applied to this one and down here to this one. Could you use the Pythagorean theorem to calculate that if we've got those two legs? Another picture here, and again, this is one of those overlapping triangles, which sometimes gives a little bit of trouble. This time they'd like you to copy it and mark that information, that it's equiangular. And how could you mark that D is the midpoint of AC? Sure, that would be a good way to do it. Now, this is not a real long problem here, but what other conclusions can you draw about BDC, this triangle, with an explanation? What else is true about it? So pause and think about the theorems presented in this lesson. This is going to be the first of several star problems we have, not only in this lesson, but future lessons. The given is really important on this. We're given that we have 10 segments, 5-lettered points. First, what polygon is it? Why isn't the red star a polygon? So we're looking at the definition of a polygon. Check that. Why does this fail? Here's the given I was looking for. All of the sides and angles of the blue polygon are equal. So keep that in mind. All the sides, so these sides are all equal. And all of the angles are equal. So from there to there, there to there. Later on in the year, we're going to call this a regular polygon. I think I may have used that phrase already. Regular polygon. So now they're asking, are the 5 line segments that form the red star, are they equal? What do you think? With an explanation. So think about that a little bit. Now they're changing it and they're saying that all the red segments, so from here to here, all of those segments are equal. Question, do you think the 5 sides of the blue polygon must be equal? So now we're wondering about these. Are these sides equal? Knowing that the red segments are equal, with an explanation. And then they're going to add one other fact. Now, not only do we know that all the red segments are equal, if they told you that all the angles up here in the stars were equal, would that make a difference? Little SAT problem here. This is a good one to ask, requiring you to think back to some previous theorems. I think it would be important to mark what's given here. We've got PQ equal to QT equal to TR equal to RS. And all they want to know is what's this angle up here. Take you a couple of steps to work this one through, but it's very gettable. Use things that you've known before as well as theorems from this lesson. Next, there's some drawing. You follow the directions here, pretty clear, and then they ask you a few questions about those triangles that you've drawn with explanations. And finally, set 3, an Escher tessellation. If you remind me, I'll bring my puzzle that I have. It's called the Schmuzzle puzzle. But there's some questions here that you'd have to kind of manipulate in your mind about that lizard.